So I want you to picture this. It is April 1930.
Okay, setting the scene.
Yeah, and we are in Atlanta, Georgia.
Probably pretty warm down there.
Oh, definitely. And we're inside this packed, sweltering lecture hall of the American Chemical Society.
Just a room full of scientists sweating in wool suits, I imagine.
Exactly, yeah. And up to the front steps, this cheerful, bespectacled chemist, a guy named Thomas Midgley.
Right, Midgley, a name that carries a lot of weight.
It really does. So he steps up, and he places this small dish of clear liquid on the table, and then he lights a simple wax candle right next to it.
Very dramatic.
It's pure theater. So Midgley leans over this dish, and he takes a deep, deliberate breath of the invisible vapor that's, rising off the liquid.
The untested, completely new vapor.
Right. He inhales it, turns to the candle, and just exhales. He blows it out.
And let me guess, he doesn't die.
He doesn't choke. He doesn't collapse. And the crowd just erupts into roaring applause.
I mean, it is a great trick.
It is. But with that single theatrical exhale, humanity had basically just accidentally armed a ticking time bomb aimed directly at the stratosphere.
Yeah, the sheer blind optimism of that moment is just staggering when you look back at it.
It really is.
Because Midgley filled his lungs with that gas to prove a point. He wanted to show, beyond a shadow of a doubt, that this new chemical was perfectly, gloriously harmless.
Right, like a miracle substance.
Exactly. And in the immediate context of that specific room, he was actually right.
Yeah, it didn't burn him.
Right. It didn't poison him. It didn't catch fire. They even gave it this friendly, accessible brand name, Freon.
Freon.
Yeah.
Such a household word now.
Yeah.
Well, today, we're going to dive into this.
Yeah.
Because we spend so much time analyzing how complex systems fall apart.
Oh, constantly.
But today, you, the listener, have provided us with this massive stack of historical and scientific material that charts a totally different trajectory.
A trajectory where we actually win.
Exactly. The mission of this deep dive today is to explore the one time in human history that we accidentally punched a continent-sized hole in the sky, stared down an apocalyptic threat, and actually managed to pull together and fix it.
We are going in search of earned hope today.
Earned hope. I love that. But to understand the magnitude of the save, we really have to understand the depth of the trap we set for ourselves.
Yeah, because it wasn't an intentional trap.
No, not at all. It wasn't built out of malice. It was actually built out of a really desperate need for public safety.
Right. To understand why Thomas Midgley was inhaling synthetic gases in a crowded room, you have to look at the terrifying reality of early refrigeration.
Which is wild to think about because today, the refrigerator is like the safest, most boring appliance in your house.
It really is. You plug it in, it keeps your produce crisp, and you just completely forget about it.
Totally.
But in the 1920s, mechanical refrigeration was a literal death trap.
Yeah, the mechanics of it were incredibly dangerous because of the gases they relied on back then.
Right, the refrigerant.
Yeah, because to make a refrigerator work, you need a refrigerant, a substance that can easily transition from a gas to a liquid and back again.
Right, absorbing heat from inside the icebox and releasing it outside.
Exactly. But the problem was, the only chemicals that could efficiently perform that phase change at room temperature in the 1920s were they were industrial nightmares.
Complete nightmares. They were using substances like sulfur dioxide, ammonia, and methyl chloride.
And these are not things you want anywhere near your food or your family.
No, definitely not. I mean, sulfur dioxide is highly toxic and corrosive.
Awful stuff.
Ammonia is suffocating, and it can be explosive under the right conditions.
Wow.
And methyl chloride is a highly flammable neurotoxin.
So you basically had companies selling these modern motorized refrigerators to households and hospitals, and they were essentially installing a ticking chemical bomb right in their kitchens.
Exactly. If a compressor malfunctioned or, say, a pipe sprung a leak while a family was sleeping, the consequences were literally fatal.
And there is a historical event in the materials you sent us that perfectly illustrates this horror.
The Cleveland disaster.
Yeah. In 1929, so literally just 1 year before Midgley's little demonstration, a massive methyl chloride leak happened at a hospital clinic in Cleveland, Ohio.
And it wasn't just a minor accident.
No, not at all. This leak resulted in the deaths of over 100 people.
It's just horrific.
Imagine the absolute terror of that. A machine designed to modernize a hospital, a machine meant to preserve vital medicines and keep food safe for patients. It ends up suffocating the very people it was built to serve.
Yeah, that Cleveland disaster sent shockwaves through the public and obviously through the industry too.
I can imagine.
The pressure on chemical manufacturers wasn't just about, like, cornering a new market. It was an existential crisis for the technology itself.
Because the public was terrified.
Exactly. People were deciding that the old-fashioned icebox, which was literally just a wooden cabinet with a block of melting ice delivered by a horse-drawn cart, they decided that was vastly preferable to a modern refrigerator that might gas them in their sleep.
Which is completely fair. I'd take the melting ice over the neurotoxin any day.
Same.
And it is so easy in hindsight to paint the chemical industry of the mid-20th century as this monolith of cynical corporate greed, right? Like executives sitting in boardrooms just cutting corners.
Right, making supervillain decisions.
Exactly. But the invention of chlorofluorocarbons, or CFCs, it was a direct, well-intentioned response to this literal crisis.
Yeah, they brought in Thomas Midgley to engineer a chemical that could cool a refrigerator without murdering the family that owned it.
So Midgley had a very specific mandate.
He did. He was an engineer, and his mandate was basically find a molecule that is non-toxic, non-flammable, and possesses the right thermodynamic properties to work in a compressor.
And he actually delivered brilliantly within those parameters.
Yeah, he really did. But the tragedy of Thomas Midgley is one of the great historical ironies.
Oh, because of his previous invention?
Yes. He had previously invented leaded gasoline to stop car engines from knocking.
Right, so he solves an immediate mechanical problem by poisoning the entire global blood supply with neurotoxic heavy metals.
Exactly. And then he solves the exploding refrigerator problem by inventing Freon.
Wow. Yeah, as the historian J.R. McNeill noted in the materials, Midgley had more impact on the atmosphere than any other single organism in Earth's history.
It's a heavy legacy. Two massive global problems solved perfectly in the short term, both of which unleashed slow-motion, invisible devastation.
And the key to Freon's success, the reason it worked so well, was his concept of inertness.
Yeah, inertness is the holy grail for a consumer chemical.
Can you break that down a bit? Like, what does that actually mean chemically?
Sure. So in chemistry, if a substance is highly reactive, it wants to combine with other things.
Like fire.
Exactly. A reactive chemical wants to catch fire, it wants to rust metal, or it wants to bond with the delicate cellular tissue in your lungs.
Okay, so it wants to do damage.
Basically, yes. But an inert substance is chemically satisfied. Its atomic bonds are so tightly locked together that it simply ignores its surroundings.
And chlorofluorocarbons are a masterclass in strong atomic bonds.
They really are. You take a carbon backbone and you bind it with chlorine and fluorine atoms.
And those bonds are just incredibly strong.
Unbreakable in normal conditions. Down here in the troposphere, the lower layer of the atmosphere where we live and breathe, CFCs react with absolutely nothing.
So you could expose them to a spark and they won't ignite?
Nope. You can inhale them, as Midgley showed, and they won't interact with your biology. They are practically indestructible down here.
Which is exactly why the world just fell completely in love with them.
Oh, an absolute love affair. Once the industry realized they possessed a gas that wouldn't explode and wouldn't poison the public, they didn't just put it in refrigerators.
It's like they put it everywhere.
They sparked an absolute revolution in consumer convenience. Car air conditioning became safe and ubiquitous.
And more profoundly, it enabled the creation of the aerosol spray can.
Yes. The aerosol boom of the mid-century is just wild to look back on.
Because CFCs were so chemically stable, they made the perfect propellant, right?
Exactly. You could pressurize them in a can with hairspray or paint or deodorant, and they would never degrade the product itself or rust the inside of the can.
They were even used in asthma inhalers, weren't they?
They were, to propel life-saving medicine deep into the lungs of patients.
That is just incredible. The ultimate proof of their perceived safety was that we were intentionally having vulnerable people inhale them.
Yeah, and by the early 1970s, the global economy was churning out hundreds of thousands of tons of these chlorofluorocarbons every single year.
So the world was practically bathing in this invisible, odorless wonder gas.
We really were, and for over 40 years, no one worried about it.
Because why would you? The defining characteristic of the chemical was its perfect stability. Why worry about a gas that doesn't do anything?
Right. But the very stability that made CFCs the safest chemicals on Earth down here in our kitchens and bathrooms, that was the exact property that turned them into an apocalyptic threat.
Yeah, this is where the story takes a turn.
Because if they had been just slightly less stable, they would have been broken down by rain or reacted with soil or degraded by the sunlight hitting the surface of the Earth.
But because they were perfectly inert, they survived.
They survived everything.
And this brings us to the year 1974. We shift from the whole consumer boom to a quiet laboratory at the University of California, Irvine.
Right, UC Irvine.
Mm.
This is where two atmospheric chemists, Mario Molina and F. Sherwood Rowland, enter the story.
And these guys weren't environmental activists looking to take down a multi-billion-dollar industry, right?
Not at all. They were just scientists engaged in pure curiosity-driven research.
They just wanted to know how things worked.
Exactly. They looked at the sheer volume of CFCs being manufactured globally and asked a very simple, elegant question.
Which was?
Since millions of tons of this incredibly stable gas are being released into the air and absolutely nothing on the surface of the Earth can destroy it, where is it all going?
It's a brilliant realization. I mean, if a molecule is indestructible, it doesn't just vanish, it accumulates.
It has to go somewhere.
So let's track the journey of a CFC molecule. Imagine someone in, I don't know, 1965 spraying a can of hairspray or a junkyard crushing an old refrigerator.
Right, a molecule of Freon escapes into the air.
Because it is heavier than the surrounding air, it doesn't just shoot up like a rocket, right?
No, it doesn't, but
Wow.
the atmosphere isn't static.
The atmosphere is a turbulent mixing fluid.
Exactly. Through global convection currents, weather patterns, and just the constant churning of the troposphere, this heavy little molecule gets swept up.
It just slowly rides the currents.
Yeah, and it ignores everything along the way. It ignores the lightning and thunderstorms, it ignores the chemical smog of cities, and it ignores the dissolving power of rain.
So over several years, it just slowly drifts upward.
Up and up, crossing the boundary of the troposphere and entering the stratosphere, which is anywhere from 10 to 30 miles above the surface of the Earth.
And sitting right there in the stratosphere is the ozone layer.
The planet's shield.
And we need to be very clear about what the ozone layer actually does, because it sounds like this abstract, invisible shield, but its function is brutally practical.
Brutally practical is a good way to put it.
Because the sun is constantly bombarding our planet with harsh, high-energy ultraviolet radiation, UVB and UVC light.
And if that raw radiation hit the surface of the Earth unfiltered, it would effectively sterilize the planet.
It holds enough energy to literally shatter DNA molecules.
Yeah. It causes skin cancer, it blinds animals, it destroys the foundational base of the marine food web. It's deadly.
But the ozone layer acts as the planet's sunscreen.
Exactly. Now, ozone is a highly unstable molecule made of 3 oxygen atoms, O3.
Okay, O3.
When high-energy ultraviolet light hits an ozone molecule, the ozone absorbs the energy and breaks apart into regular oxygen.
And then what?
Then it quickly reforms back into ozone. It is a continuous natural cycle that harmlessly dissipates the sun's deadly radiation as heat.
Okay, so our little indestructible CFC molecule, which has survived a years-long journey through the lower atmosphere, finally floats up into this protective ozone layer.
Right.
For its entire existence, it has been shielded from the worst of the sun's radiation by the atmosphere above it. But now, it crests the top of the ozone shield.
It reaches the top floor.
Yeah. And it is suddenly exposed to the raw, unfiltered fury of solar ultraviolet light.
And that UV light carries enough kinetic energy to do the one thing nothing on Earth could do.
It acts like a microscopic sledgehammer.
Exactly. It cracks the CFC molecule wide open.
And when that incredibly strong carbon-chlorine bond is finally shattered by the UV light, the CFC molecule releases its payload.
It drops a free, highly reactive chlorine atom directly into the ozone layer.
And unlike the CFC it came from, a free chlorine atom is violently reactive, right?
It is aggressively unstable. Chlorine has a profound chemical affinity for ozone.
It wants to bond with it.
Desperately. So when this free chlorine atom bumps into an ozone molecule, it forcefully rips one of the oxygen atoms away.
So the O3 molecule is destroyed.
Yes. Leaving behind regular breathable oxygen, O2, which does absolutely nothing to block UV radiation.
Now, if one chlorine atom destroyed one ozone molecule, that wouldn't really be a crisis, would it?
No, the atmosphere is massive. A simple one-to-one exchange wouldn't cause a noticeable dent.
But when Molina and Rowland mapped out the chemistry, they discovered something horrifying.
Yeah, the destruction wasn't a one-to-one exchange. It was a catalytic cycle.
The catalytic cycle. That's the mechanism of the apocalypse right there.
It really is, because after the chlorine atom destroys the ozone molecule by ripping away an oxygen atom, a subsequent reaction causes the chlorine to drop that stolen oxygen atom.
Oh, so the chlorine atom is suddenly perfectly free again.
Exactly. It is not consumed in the chemical reaction. It acts as a catalyst.
It moves on to the next ozone molecule, tears it apart, drops the oxygen, and moves on again.
Over and over and over.
It is a molecular wrecking ball. Materials used a really good analogy here. Imagine tossing a single indestructible bowling ball into a cosmic alley.
Right.
It doesn't just hit the pins once and stop. It bounces off the walls, knocking down a pin, then another, ricocheting forever.
Yeah, a single free chlorine atom can survive in the stratosphere for decades. Decades. Continually tearing apart tens of thousands of ozone molecules before it finally sinks back down into the lower atmosphere.
Tens of thousands from just one atom.
Exactly. So when Melina and Roland looked at their calculations back at UC Irvine, the math was just chillin'.
Because we were pumping millions of tons of CFCs into the atmosphere every single year.
Millions of tons. And each molecule contained multiple chlorine atoms.
And each of those atoms had the potential to destroy up to 100,000 times its own weight in planetary sunscreen.
The math was undeniable, and it was terrifying.
There is this famous, heavily cited anecdote in the source material about the moment this reality set in for them.
About Roland and his wife.
Yes. F. Sherwood Rowland goes home to his wife, Joan, after reviewing these catalytic destruction cycles. And she asks him, how the research is going.
As you do over dinner.
Right. And Rowland reportedly looks at her and says, "The work is going well, but it looks like it might be the end of the world."
And the craziest part is, it wasn't academic hyperbole. He meant it literally.
If their math was correct, the continued mass production of CFCs would eventually thin the ozone layer so severely that complex life on the surface of the Earth would become unsustainable.
Agriculture would literally wither under the UV radiation.
Global food supply chains would collapse.
And human health would face just an unmitigated disaster of radiation exposure. Rates of skin cancer and cataracts would skyrocket.
So faced with this existential math, Melina and Roland do exactly what scientists are supposed to do.
It sounded the alarm.
They write up their findings, and they publish their paper in the prestigious journal Nature in 1974.
They lay out the entire mechanism for the world to see.
The atmospheric mixing, the UV breakdown, the catalytic chlorine cycle. They present humanity with the literal blueprint of its own destruction.
And the world doesn't really stop.
Yeah, that's the frustrating part. The immediate reaction for the chemical industry is just this fierce, organized denial.
Well, you have to view it from the perspective of the industry in the 1970s. The CFC market was worth billions of dollars globally.
Entire sectors of the economy were built on it.
Exactly. Refrigeration, automotive, cosmetics, pharmaceuticals, they were all dependent on these chemicals.
So when two academics publish a theoretical paper claiming that invisible gases were doing invisible things miles above the clouds, the industry pushed back aggressively.
They pointed to the lack of direct observational evidence, which at the time was true. It was all theoretical math.
Right. They argued that you cannot dismantle a cornerstone of modern industrial society based on a computer model and laboratory math.
And honestly, that highlights a fundamental flaw in human psychology.
How so?
We are just not evolutionarily equipped to panic over abstract, slow-moving, invisible threats.
Yeah. If a tiger's in the room, we run.
Exactly. But if a math equation says we will slowly burn to death in 50 years due to ultraviolet radiation, we form a committee.
We ask for more studies.
Right. To make the global community actually care, the threat couldn't just exist on a chalkboard. It needed to be violently visible.
Humanity needed to see the monster.
And the transition from abstract theory to visceral terror happens 11 years later, in 1985.
Okay, 1985.
But the most fascinating aspect of this discovery is where it actually comes from.
Right, because it doesn't come from a multi-billion-dollar NASA supercomputer.
No, it doesn't. It comes from 3 researchers stationed in the most hostile, remote environment on the planet.
We moved to the British Antarctic Survey Station at Halley Bay, Antarctica.
Talk about remote.
It's this desolate, freezing outpost on the ice. 3 scientists, Joe Farman, Brian Gardner, and Jonathan Shanklin, are there, conducting routine foundational measurements of the atmosphere.
And they were doing it using a piece of technology called a Dobson spectrophotometer.
Which sounds incredibly high-tech, but the fundamental design of this instrument actually dates back to the 1920s, right?
Yeah, it wasn't some sleek digital sensor. The Dobson spectrophotometer is a brilliant, heavy, mechanical piece of optical engineering.
What does it actually look like?
It looks a bit like a bulky metal telescope pointing at the sky. What it does is measure the exact intensity of sunlight reaching the ground.
Okay, so it's looking at the sun.
Right. Specifically, it uses a series of prisms and optical wedges to isolate two distinct wavelengths of ultraviolet light.
Why two?
Because one of these wavelengths is heavily absorbed by stratospheric ozone, and the other wavelength passes right through the ozone completely untouched.
Oh, that's clever. So by pointing this antique-looking machine at the sun, they capture these two wavelengths.
Exactly. And by comparing the ratio of the light that gets absorbed versus the light that makes it through, they can calculate a highly accurate measurement of exactly how thick the ozone layer is directly above their heads.
It's analog, labor-intensive mathematics.
Very labor-intensive. But in the early 1980s, Farman, Gardner, and Shanklin start noticing something deeply wrong with their spring measurements.
Something of the data.
Yeah. Every September and October, as the sun finally returned to Antarctica after months of total winter darkness, the ozone levels overhead weren't just fluctuating.
That were plummeting.
The drop was so sheer and precipitous that they initially assumed their vintage instrument was finally breaking down.
I mean, you would, right? Up to a third of the ozone column was just missing.
It's the ultimate scientific nightmare. Your data is so bad, you assume it has to be a hardware glitch.
They actually ordered a brand new replacement Dobson instrument to be shipped down to the ice.
Just to double check.
Yeah, they set it up, calibrated it, pointed it at the sky, and it told them the exact same horrifying story.
The sky above Antarctica was literally emptying out.
So in May 1985, they published their own bombshell paper in Nature. They announced to the world that an area of the ozone layer the size of a continent was disappearing every single spring.
They had discovered a literal hole in the sky.
And this discovery raises two massive questions based on the sources.
Yes, the why and the how.
Exactly. First, why Antarctica? Why did the hole rip open over the most isolated, unpopulated continent on Earth when the vast majority of CFCs were being sprayed and leaked in the heavily populated Northern Hemisphere?
Right. If you spray a can of hairspray in New York, why does the sky break over the South Pole?
I was wondering this exact thing while going through the materials. It just seems so counterintuitive.
The answer lies in the extreme, brutal meteorology of Antarctica itself.
Okay.
During the Antarctic winter, the continent is plunged into total darkness for months. The air above the ice grows so profoundly cold that it creates a massive swirling cyclone in the stratosphere called the polar vortex.
The polar vortex.
Yes. This vortex acts like an atmospheric quarantine wall. The air trapped inside it is completely isolated from the rest of the global atmosphere.
And it gets cold.
Unbelievably cold. The temperatures plummet to below minus 78 degrees Celsius.
Minus 78. That is unimaginably cold. And this extreme cold triggers something unique in the stratosphere, right?
Exactly. Normally, the stratosphere is completely dry. There are no clouds up there.
Right.
But when the temperature drops that low inside the polar vortex, the trace amounts of water vapor and nitric acid actually freeze into these shimmering, iridescent ice formations known as polar stratospheric clouds.
Polar stratospheric clouds. And this is the missing piece of the puzzle, isn't it?
It is. The ice crystals in these clouds act as physical, flat surfaces.
So when those inert CFC molecules drift into the vortex...
The ice clouds provide a surface for chemical reactions to accelerate at terrifying speeds.
Wow. So the chlorine atoms gather on the ice during the dark winter.
They just sit there, accumulating. And then when spring arrives and the first rays of sunlight hit the ice...
The sunlight provides the energy, and the accumulated chlorine goes into a hyperactive catalytic frenzy.
It destroys the ozone layer in a matter of weeks, carving out a massive hole.
Just ripping through it.
Yes.
Yeah.
Once the summer warms the air, the vortex breaks down, the ice clouds melt, and ozone-rich air from the rest of the planet rushes in to heal the hole.
But that lowers global ozone levels in the process, right?
Exactly. And then the next winter, the cycle repeats, tearing a larger hole every single time.
Okay, so that perfectly explains the why. But the second massive question from the sources is about how we found it.
The NASA question.
Yeah, it's 1985. NASA has satellites orbiting the Earth. We have sophisticated multi-million-dollar pieces of orbital hardware explicitly designed to monitor atmospheric conditions.
We were actively watching the sky.
Right. So how is it possible that three guys in parkas, manually operating a 1920s prism instrument on the ice, saw a continent-sized hole in the atmosphere before NASA's satellites did?
This is one of the most profound lessons in the history of data science, honestly.
The sources go deep into this.
Yeah, because there is a popular myth out there that NASA's computers were just too primitive, or that they just missed the hole.
But that's entirely false.
Completely false. NASA's satellites were working perfectly. The sensors had actually been recording the catastrophic drop in Antarctic ozone for years.
Wait, for years?
Yes. The blind spot wasn't in the hardware, it was in the human assumptions programmed into the software.
The algorithms.
Yeah.
The data processing back on Earth.
Precisely. NASA's satellites were beaming back oceans of data far too much for humans to review manually.
Of course.
So software engineers wrote quality control algorithms to sift through it. When writing the code, the programmers had to establish a baseline of reality.
Right, they had to tell the computer what was normal.
Exactly. They looked at historical atmospheric data and concluded that ozone levels naturally fluctuate, but they never physically drop below a certain threshold, say, roughly 180 Dobson units.
So they assumed anything below that number was mathematically impossible.
They hard-coded their assumptions into the machine. They basically instructed the software. If the satellite sensor reports a value lower than this threshold, it is scientifically impossible. The sensor must be degraded, or a cosmic ray hit the electronics, or there's transmission interference.
So what did the software do?
It was told to flag the extreme low data as an instrument error and just filter it out of the main reporting.
Oh, that is chilling. The machine saw the apocalypse happening in real time. It accurately measured the end of the world, and the human programming patted it on the head and said, "That can't be right. Put that in the trash."
The data was flagged and just set aside. It wasn't until Farman's team published their ground-based measurements in 1985 that NASA scientists realized what they had actually done.
They must have scrambled.
They went back to their flagged erroneous satellite data, and there it was.
Oh,
The satellites had been screaming at them for years, mapping this terrifying, growing void in the ozone layer, and they had programmed themselves to ignore it.
but once NASA corroborated the British ground data with their satellite imagery, everything changed, right?
Overnight, the abstract threat now had a face.
You could put a false color satellite image of it on the evening news.
Yes, it was no longer a dense chemical equation about catalytic chlorine cycles. It was a giant, terrifying purple and blue bruise growing over the South Pole.
It was a visible hole in our planet's primary defense system.
And that image catalyzed a level of global panic and political mobilization that we had never seen before, and frankly, haven't quite seen since.
The speed of the international response is what makes this story the ultimate benchmark for global cooperation.
It really is the gold standard.
From the undeniable public proof of the hole in 1985, it took just 2 years to architect, negotiate, and sign the Montreal Protocol in 1987.
Which is just staggering.
Let's pause and really appreciate that timeline. 2 years to take a multi-billion-dollar cornerstone of the global chemical and manufacturing economy, bring the entire world to the table, and agree to phase it out of existence.
It's whiplash speed for international diplomacy.
We are so used to decades of gridlock and endless summits today. How did they actually pull this off in 2 years?
Well, the political alignment was extraordinary, and it required some incredibly unlikely champions.
Okay, like who?
Well, in the United States, you had Ronald Reagan in the White House.
Right.
He was a staunch conservative, heavily aligned with industry, and fundamentally opposed to massive governmental regulation. On paper, his administration should have fiercely opposed crippling a major chemical sector.
So why didn't he?
Reagan had recently undergone surgery for skin cancer. He had basal cell carcinomas removed from his nose.
Oh, wow. Suddenly, the threat of an eroded ozone layer causing skyrocketing rates of skin cancer wasn't just an abstract scientific white paper.
Exactly. It was deeply physically personal to the leader of the free world.
That is a massive wild card in history.
It really is. And across the Atlantic, you had Margaret Thatcher as the Prime Minister of the UK, the Iron Lady.
Another fierce champion of deregulation and free markets.
Yes, but Thatcher held a university degree in chemistry from Oxford.
I did not know that.
Yeah. So when she was presented with the data from the British Antarctic Survey and the mechanisms outlined by Molina and Rowland, she didn't see a political wedge issue.
She saw the science.
Her scientific training allowed her to look at the raw data and understand the terrifying reality of the chemical equations.
So you have these two massive conservative geopolitical heavyweights throwing their weight behind strict environmental regulation, driven by this crazy mix of personal experience and scientific literacy.
It was the perfect storm for action.
But they still had to convince the rest of the world, right? Because developing nations rightfully pointed out that the wealthy nations got to build their modern economies using cheap CFCs for refrigeration and infrastructure.
Right. And now, just as developing nations were trying to modernize, the wealthy nations were pulling the ladder up and saying, sorry, you can't use this cheap technology. You have to buy expensive alternatives.
That feels incredibly unfair.
It was. And that was the greatest hurdle to a global treaty. But it is also where the Montreal Protocol proved its genius.
How do they solve it?
The negotiators recognized the fundamental inequality of the situation. To solve it, they established the Multilateral Fund.
The Multilateral Fund, what was that?
The wealthy developed nations agreed to contribute billions of dollars into a central fund specifically designed to pay for the developing world's transition away from CFCs.
Okay, wow.
And it wasn't charity, it was planetary self-preservation. They understood that a CFC molecule released in Mumbai damages the ozone layer just as much as one released in Manhattan.
They actually put their money where their mouth was.
Yes.
And it worked.
Let's look at the hard numbers from your materials because they are staggering. The Montreal Protocol on substances that deplete the ozone layer became the first treaty in United Nations history to achieve universal ratification.
Universal. Every single recognized nation on Earth, 198 parties by 2009, ratified the treaty.
That is hard to comprehend. The deep ideological divides of the Cold War, the bitter economic friction between the global North and the global South, all of it took a back seat to the shared, terrifying realization that the sky above us was breaking.
Because we all share the same sky.
Exactly.
I really want to emphasize the success of this for you, the listener. It sounds like a utopian fairy tale, but it is hard data.
Oh, absolutely.
Since the treaty went into effect, the global community has phased out roughly 98% of all ozone-depleting substances compared to 1990 levels.
We practically eliminated an entire class of foundational industrial chemicals.
But the real question is, did it save the sky? Is the hole actually closing?
The recovery is actively happening, yes, though it is a slow process because CFCs are so incredibly long-lived in the stratosphere, as we discussed.
Right, they stick around for decades.
According to the 2022 Scientific Assessment of Ozone Depletion, if current policies remain rigorously enforced, the global ozone layer is projected to return to 1980 levels, which is the baseline before the hole appeared, by around 2040.
2040? That's not that far away.
Over the Arctic, full recovery is expected by roughly 2045. And over the Antarctic, where the damage was most severe due to the polar vortex, we expect the hole to permanently close by about 2066.
So within many of our lifetimes, or our children's lifetimes, the damage will be entirely erased.
Entirely. And we are already seeing the evidence. By late 2025, the Antarctic ozone hole was measured as the fifth smallest since 1992, and it closed early on December 1st of that year.
So it's demonstrably shrinking.
Yes. While year-to-year weather variations cause the hole size to fluctuate, the long-term, multi-decade trend line is undeniable. The atmosphere is actively healing.
That is just incredible.
And there is a massive unintentional side benefit to this treaty that is it's incredible.
A climate benefit, right?
Yes. It turns out that chlorofluorocarbons are not just ozone destroyers, they are also unbelievably potent greenhouse gases.
How potent?
A single molecule of CFC can trap thousands of times more heat in the atmosphere than a molecule of carbon dioxide.
Thousands of times.
Yes. So by banning CFCs to save the ozone layer, we accidentally enacted one of the most effective climate treaties in history.
That is wild.
Climate modeling estimates that the Montreal Protocol has avoided roughly 0.5 to 1 full degree Celsius of global warming by mid-century.
When you think about how hard we are fighting right now to prevent even fractions of a degree of warming, realizing we already dodged a full degree by accident is just mind-blowing.
It really is. The alternative timeline, the world we avoided, is apocalyptic.
Yeah, if Molina and Roland hadn't done the math.
If Farman's team had ignored their antique instrument.
If the global community had spent 40 years arguing over the data.
We would be living in a world where going outside in the summer sun for a few minutes would cause severe burns. Agriculture would be failing globally. It is a profound triumph of human cooperation.
But of course, real planetary maintenance is not a spotless, magical fairy tale.
No, it rarely is.
We have to look at the asterisks.
Right.
We have to ensure this deep dive doesn't just become a smug victory lap, because maintaining the Earth is a messy, ongoing job.
It's very messy.
The Montreal Protocol is a living document, and according to the sources, it had to deal with 2 massive wrinkles in the decades following its signing. Let's tackle the first wrinkle. the replacement chemicals.
Right, because when we banned CFCs, the global demand for refrigeration and air conditioning didn't just disappear.
People still needed their ice cream.
Exactly. The chemical industry had to pivot rapidly, and they transitioned primarily to a class of chemicals called hydrofluorocarbons, or HFCs.
HFCs, okay.
And from the strict perspective of the ozone layer, HFCs were the perfect solution. They contain no chlorine atoms. They cannot trigger the catalytic destruction of ozone.
So we swapped out the toxic chemicals, we saved our ice cream, and we saved the planetary sunscreen. What's the catch?
The catch is the molecular architecture of HFCs. While they completely ignore ozone, their chemical bonds vibrate at very specific frequencies.
What does that mean?
When sunlight hits the Earth and reflects back up towards space as infrared heat, those HFC molecules absorb that specific infrared frequency perfectly. They act like a thermal blanket, trapping the heat in the lower atmosphere. So we solved the immediate ozone crisis, but our solution inadvertently accelerated the global climate crisis.
It's the classic engineering dilemma. You plug a leak in a sinking boat by ripping a plank off the hull to cover the hole. You fix one problem by exacerbating another.
Exactly.
Did this break the treaty?
It tested it, definitely. But this is where the genius of the Montreal Protocol's framework shines.
Because they didn't just give up.
No. Instead of throwing their hands up in defeat or letting the climate crisis worsen, the global community used the existing trusted legal framework of the treaty.
They went back to the table.
In 2016, they reconvened in Kigali, Rwanda, and passed the Kigali Amendment.
The Kigali Amendment.
Yes. They formally adapted the treaty to phase down the production and consumption of these HFC greenhouse gases. They recognized the new threat and fixed the fix.
That is resilience. But the second wrinkle is even more illuminating about human nature, I think.
The rogue emissions.
Yeah. Around 2018, atmospheric scientists who monitor global air samples detected something deeply alarming. A sudden, unexplained spike in the atmospheric concentration of a specific chemical called CFC11.
And this was a massive red flag.
Because CFC11 is a first-generation ozone-depleting substance.
Exactly. Under the Montreal Protocol, its production was supposed to have been completely globally phased out years prior. No nation on Earth should have been manufacturing it.
But the scientific monitoring stations were picking up fresh emissions.
Yes. Through complex atmospheric tracking and wind modeling, scientists actually traced the source of these rogue emissions to heavily industrialized regions in Eastern Asia.
So someone was cheating.
They were. A factory, or a network of factories, realized it was cheaper to use the banned, highly effective CFCs to make things like foam insulation.
Because it's a good chemical for that, if you ignore the atmosphere.
Right. So they quietly spun up illegal production lines, assuming the atmosphere was so vast and the sky so big that no one would ever notice their invisible emissions.
And this moment presents a crucial philosophical question for anyone studying international agreements, right?
Yes. How do you interpret failure within a system?
Because the cynical, purely pessimistic take is to look at those rogue emissions and say, look, humans are inherently selfish. Someone cheated for a quick profit. Global treaties are toothless, and the whole system is a failure.
It's very easy to jump to that conclusion.
But that completely misreads what a treaty actually is.
Yeah.
A treaty isn't a magical spell you cast over the earth that physically prevents bad behavior.
It is an agreed-upon framework for accountability.
Exactly. The rogue emissions didn't prove the system failed. They proved the system's alarm network functioned exactly as designed.
The scientific monitoring caught the cheating.
Yes. The international community took that data and confronted the findings.
And domestic authorities in the offending regions, under intense international pressure, cracked down on the illegal factories, shutting them down and confiscating the materials.
And the data proves the crackdown actually worked. In the years following that discovery, the emissions of CFC11 dropped dramatically back down to expected levels.
The alarm went off, the authorities responded, and the trajectory was corrected.
To me, that makes the victory of the Montreal Protocol so much more potent. It proves it can handle the methy, greedy reality of human nature, correct for it, and keep functioning.
It's not propaganda, it's a working system.
As we bring this deep dive to a close, I want to take a moment to look back at the individual human lives caught in this massive atmospheric drama. Because the fates of the people who started this and the people who ended it are incredibly poignant.
It is hard not to think about Thomas Midgley. He passed away in 1944.
He died entirely unaware of the planetary bill his miracle gas was racking up.
He went to his grave celebrated as a genius inventor. a man who tamed the explosive dangers of early refrigeration.
He never knew that by breathing in that freon and blowing out that candle, he had unwittingly armed a chemical weapon that would nearly strip the Earth of its protective shield.
And you contrast Midgley's fate with the chemists who discovered the bomb, Mario Molina, F. Sherwood Rowland, and their colleague Paul Crutzen, who did foundational work on the atmospheric chemistry of nitrogen oxides.
When they published their paper in 1974, they were mocked.
They were sidelined by massive industrial lobbies. They had to spend a decade fighting to convince the world that an invisible threat was real.
But they lived long enough to see the world actually listen.
They lived to see the data from Antarctica vindicate their math.
They lived to see the global community sign the Montreal Protocol.
And in 1995, the three of them stood on a stage in Stockholm and shared the Nobel Prize in chemistry.
They sounded the alarm, the world woke up in time, and they lived to see their warning heeded.
It is one of the rarest, most beautiful narratives in the history of modern science. The prophets of doom were actually listened to in time to prevent the doom.
If we synthesize this entire journey from your sources, from the naive chemical age optimism of the 1930s to the chilling chalkboard arithmetic of 1974, to the terrifying satellite blind spots of 1985, and finally to the hard-fought diplomatic resolve of 1987, what is the core lesson? What is the recipe we take away from this?
The takeaway isn't a naive belief that humans are inherently great or that everything will always work out. We are remarkably good at creating existential messes.
Clearly.
But this history is a proven, documented recipe showing that humanity is absolutely capable of solving planetary-scale crises. The recipe requires three distinct elements.
What are they?
First, the science must be rigorous, clear, and fiercely defended in the public sphere.
Okay.
Second, practical technological alternatives must either exist or be aggressively developed and funded.
We needed an alternative to CFCs.
Exactly. And third, political will must align across deep ideological and geographical borders. When you combine clear science, practical solutions, and shared political courage, we are capable of moving mountains.
Or in this instance, we are capable of healing the sky.
Exactly.
It is the absolute definition of earned hope. We don't have to guess if we can save the world from our own mistakes. We have the hard data proving we've already done it once. I want to leave you, the listener, with a deeply resonant image to ponder on your own after this audio stops.
It's a powerful thought.
Think about this. Somewhere high over the freezing expanse of Antarctica tonight, a wound the size of a continent is slowly, quietly closing. No one will feel it happen. No one will stand out on the ice and cheer as the atmospheric chemistry finally balances out.
Because it's invisible.
Right. It is being knitted shut by a decision made decades ago by people who will mostly be dead before the healing is completely finished. It is not a fairy tale. It is a precise, ongoing measurement. And the sky is keeping the receipt. Thank you for joining us on this deep dive. Carry that hard-earned hope with you.